Welcome, everyone. Thank you for joining us for today's webinar, Asset Integrity Programs in Support of the PSM Program for Egypt, presented by Dan Bennick and Mike Nugent. Now, for today's webinar, I want to go over a few housekeeping items. First, we want to respond to your questions following this webinar. Please type questions into the Q&A box in the Zoom control panel, and our presenters will respond to those questions. At the close of our webinar today, please provide feedback by responding to our survey, where you can provide recommendations for today's presentation and future webinar topics. We're excited to have Dan Bennick and Mike Nugent present today. So without further ado, I will turn the time over to Wayne Repich, who is the Global Director of Business Development and Marketing and Communications, and also the Key Account Program Director for Baker Risk, to make a few remarks.
Thank you, Naomi. Hello to everybody in Egypt, our friends, our good friends there and around the world. Thank you for joining us on our third webinar in our series. We're very excited to be here once again with you and appreciate your participation. Thank you again to the ministry for their support, and Engineer Ala Hagar and Wessem Sakar. They've been very supportive throughout our three webinars, and we look forward to continuing that relationship with them. I do want to introduce our special guest, who you probably can see on camera right now, Amr Hassan, who is no stranger to you in Egypt. I'm sure you're very familiar with him. He's part-time with Baker Risk as a senior principal consultant. Go ahead and say hello there.
Hi, everybody. How are you?
Good. And you'll be hearing from Amr a little bit later, towards the end of the session. And the session will run about an hour and a half in total. So that'll include the Q&A that we're going to have. The content is a little bit over an hour. From Dan and Mike, we'll go ahead and have a few questions. I know that just based on the past experience, we typically get loaded up with questions in the chat or in the Q&A. So please do continue that. We will not be able to get to all of them. I know that for a fact. So what we will do will be the same thing we've done in the past, which is within 2 weeks, we will send out by email all the questions asked, as well as all the answers, along with any other resources that we feel might be of interest to you based on those questions and your input, and also any other resources that we can. We'll include that at that time. Okay, so without further delay, I will go ahead and turn this over to Dan. And again, thank you to everybody in Egypt for your continued support. We're glad you're here and look forward to continuing our relationship with you as well. Dan?
Well, thanks. Thank you, Wayne and Naomi. And on behalf of Baker Risk, thank you for joining us today. Both myself and Mike are very looking forward to presenting this topic that is something that is dear to our hearts, as we've spent most of our careers dealing with asset integrity issues and for the purpose of maintaining reliable plant operations. So we look forward to that. And with that, I want to kind of go into what we hope to accomplish during our time together. We're going to be covering a lot of material in a very short time. We want to give an overview to understand why an asset integrity management program is needed, often referred to as AIM. We want to discuss specifically some of those elements of a good mechanical integrity or asset integrity program. We've decided to talk about damage mechanism reviews. Both Mike and I have been involved in that, and we think that's an important part of a good asset integrity program. Related to that, we're just going to kind of at a high level talk about some of those potential damage mechanisms that could limit the lifetime of your equipment, which you're very concerned about. And then we want to propose a best practice that we have observed from some of our customers that we work with on looking at investigations. So as far as that's our objectives, but here again is some of the outline of what we will be discussing. We'll talk about the importance again, who your presenters are, a case history to kind of whet our appetite, and do some comparing and contrasting of PSM, process safety management, mechanical integrity, and an asset integrity program. And those key elements of that, as I mentioned, damage mechanism reviews. Some of you may have been familiar with that. We want to share what we consider a shining star of an application of an asset integrity program that we have been leading for 3 years now globally, and that is for the ammonia and fertilizer joint industry program. And Mike's going to go into the importance of inspection programs, and because that's something dear to his heart. And then, as I mentioned, we'll talk about a best practice about trending near misses and failures. A little bit about myself. From the video, you might recognize that I'm not a young engineer anymore. I have over 40 years of experience working in many industries. Started my career actually working in a refining industry, working onshore, offshore, in the plant. Cut my teeth on doing investigations for refineries and for production facilities, been in the North Sea. Through those experiences, I have become a subject matter expert in the area of corrosion and materials evaluation. I'm a certified fire and explosion investigator, as well as a professional engineer. Have worked around the world dealing with mechanical integrity issues abroad, because things do happen, and we as a company have been sought out for that, and I've been honored to participate in that, and have been involved in many committee works, and this, again, the subject matter expert for the ammonia and fertilizer joint industry program. Again, that's just a little bit about me. I also oversee our materials lab here in San Antonio, Texas, and have a great group of experts that I work with. So now, Mike, why don't you introduce yourself?
Thanks, Dan. My name is Mike Nugent, and I also have been in the asset integrity business in petrochemical, fossil, nuclear, LNG for over 40 years. 30 of that I've spent in plants, both refineries, chemical plants, and power plants, as corrosion materials inspector up to section head and manager of integrity in various plants. So I've worked with Exxon, ConocoPhillips in their programs. I had 5 years in Exxon, and I spent a lot of time in Exxon plants. I've had a principal mechanical integrity role as a consultant for about 15 years worldwide. And in that time as a international consultant, I had a lot of time in the various regions to see what kind of programs are being implemented, specifically in the Arabian Gulf area. I've done a lot of work with Saudi Aramco, with ADNOC, AdGas. I've also done damage mechanism reviews and CCDs for existing plants and pre-startup plants for SABIC and SIPChem. And had a lot of time. I've spent a little bit of time with EBIC also, going through some of their initial ventures into RBI probably about 10 years ago. So I am well traveled, and I had the experience of looking at many programs of asset integrity management and implementations and damage mechanism reviews. I've been fortunate enough to be with a company that basically started the risk-based inspection and fitness for service software and program back almost 15 years ago now, and we've implemented those programs and other programs around the world. Not only am I a practitioner of non-destructive testing, I do hold a patent on a non-destructive testing methodology in ultrasonics, and I'm also a fellow in the ASNT, and I've been on the board of directors of 3 different non-destructive testing companies, both service providers and equipment providers, so I know the applications and I know the development and the technology very well for non-destructive testing, its strengths, its limitations, and its abilities to assist us, and its abilities to confuse us. So hopefully I try to use the NDE technology that's most appropriate for the plant situation. I do have both a bachelor's and a master's degrees in material science and engineering. And I had the privilege of being a professor in a local university, technical institute for 20 years, teaching mechanical engineering, which keeps you young and keeps your perspective very, very fresh, because students do not let you get old, and you have to maintain very current knowledge and capability of your trades. I've been involved with API for over 20 years, and many other national ASNT and NACE. So that's my credentials, and we'll move on right now to some of the technical details.
Well, thanks, Mike. And Mike will be speaking to us shortly. So I want to start us out with a storage tank concern that happened a few years back that we and I specifically was involved with. I set the tone because this will be an example of some things that went wrong in an asset integrity program. This was a tank that was previously had been in service in a sulfuric acid situation for 22 years, and it was decided to put it into a different application, specifically into a spent sulfuric acid condition. Spent sulfuric acid is basically the fact that there's hydrocarbons now in that sulfuric acid, and it was used from an alkylation process. So therefore, this tank got changed in application to a spent sulfuric acid tank. And in addition to that, multiple repair wells had been done, not only at the base of the tank, but also on the side of the tank and even on the roof of the tank. And on the day of this particular incident, inert gas was flowing in the tank because there was some repair work going on in the vicinity of the tank. This is a very large tank farm. You can see in this picture some of the other tanks. There was actually 6 tanks in this tank farm. So there was hot work activity going on above this particular tank. And a failed tank was connected to another tank. And that's important because there was natural flow that had occurred to allow air to go into this particular sulfuric acid tank, unbeknown to the hot workers at the time. As they were doing work, unfortunately, and a very tragic fatal situation occurred where an explosion, what we would call a deflagration, occurred inside the tank, rattled the tank, and literally lifted this tank off its base into the air and threw it on its side. As you can see here, this was a view that I actually was in a lift taking pictures of this particular tank. What we determined in our investigation, a very complex investigation, took many years before it finally all settled, but at a very high level, air had entered into the tank. You had a spent sulfuric acid, so vapors, hydrocarbon vapors were present. And then in this vapor space, there was a fuel air mixture such that a spark from the hot work had thrown itself into the tank because there were holes on top of this tank. Not only were there holes on top of the tank, but as I mentioned, you can see in the lower picture, you can actually see some of those holes that were on the top of the tank. So it was just a spark basically that got in there, and it caused that failure to occur. Later on, we're going to be talking about damage mechanisms, and I show this slide because just to point out that sometimes things are not as simple as you may think, and I have my cursor on here. So just to show you the subtlety here, at 100% of concentrated acid, the corrosion rate is actually less than when I'm diluted. And so you can see here at this 20 over 200 mils at a certain temperature. So the reality of the situation, this situation of this tank actually had rainwater get in there. And so the sulfuric acid became more diluted than the concentrated, and therefore the corrosion rate was much higher. that was a contributor to some of the observed corrosion. The point being is you have to understand potential damage mechanisms to fully prevent something from happening. So at a very high level, here's a few things you could call lessons learned as it was related to an asset integrity considerations. One, this tank was designed for sulfuric acid. It was not designed for spent sulfuric acid. Therefore, it was not a frangible roof design. What that means is a frangible roof will intentionally fail if the pressures get too high. Well, the pressures did get high, but because the roof was a solid non-frangible, it basically lifted it off the ground. Otherwise, the tank would have just failed at the top. This particular tank did not have a robust integrity program, obvious of the corrosion that was evident. There was inspections that were done, but it was inadequate because of corrosion that actually occurred under insulation. Many of you probably are familiar with CUI, corrosion under insulation. As I mentioned, the damage mechanism of diluted sulfuric acid was not fully understood. And although they had a purge system, the purge was inadequate. And so, you know, you could say, well, I checked that box, we purged it. Well, the purge was not adequate, obviously, because it lit off and it was in the flammable range. In the hot work, although there were hot work orders that were signed off, they were not fully adhered to, and some of the dangerous situations were not fully accounted for. So just as an example of a storage tank, although these are many, many things that could have been addressed, it just reinforces the necessity of having a good asset integrity program. Many of you here on this particular webinar have a process safety background, and just to put us all on the same page, it's a disciplined framework of looking at the hazards and applying those good designs, good engineering practices, operating practices, therefore to present and to minimize the hazards that definitely can occur with toxics, with fires, with explosions, potential injuries, and also just the loss of production, which is very costly to many of us. So PSM has been in the United States. I know it's in the Egyptian world. It's a way, again, of ensuring that the integrity of your equipment and the systems that monitor that are in place. And not only in place, but I'm going to emphasize something here. You have a written program. And I'm going to also emphasize it's not just written, but it's also implemented. I have audited several places that have written programs, but their implementation falls short. The real desire is you do not want to have a loss of containment like this storage tank. It could be a pipe, it could be a vessel, it could be anything, but you want to keep the chemicals basically in your pipe, in your asset. And so that's why you do your asset integrity. It's to have those procedures, to have those controls. We want to keep the contents in the pipe and keep it under control at all times. What you're seeing is another incident that our team was involved with a few years back of a brittle catastrophic failure. Unfortunately, catastrophic failures like brittle failures there's very little warning. And therefore, that's why you have to have a good asset integrity program to know what scenarios might cause a brittle fracture. In this particular case, there was a weld that was performed that was a poor quality weld, and under operating conditions of less than a day of operating, it catastrophically failed. So an asset integrity program would be controlling that. Just to show you some statistics, mechanical failures, if you look at this pie chart, you'll see that a lot of your failures are predominantly, like over 50% are due to mechanical failures or operation related. In fact, another survey stated that 50% of major losses of containment were primarily due to aging of equipment, due to either erosion, corrosion, or fatigue. And I would agree with that, having worked with many of the damage mechanisms that can cause concerns, such as fatigue, cyclic loading, higher temperature exposures, corrosion, and sometimes velocity effects. These are all things that are taken into account. Well, in the process safety regulations, both in the UK, in the United States, and now even in Egypt, there are standards and guidelines that are put out there. And those have come because of incidences that have occurred worldwide. It all kind of started in the UK and in the United States in the late 80s, early 90s because of incidences. OSHA in the States created a law referred to as 1910.119. Under that was mechanical integrity. And I'm aware and have seen some of the Egypt PSM related standards and guidelines shown here that you are looking at and considering and trying to implement in some of your plans. So there are the original 1910 elements included these 14 elements. Many of these, in fact, if you think about the incident I just talked about, there was several of those that were not adequate. One, there was a management of change. They changed the tank to a different service. Contractors were working were not, they had a hot work permit, but it wasn't adequate. Training was an issue. The integrity of the tank, the emergency response was a factor when the incident occurred. So you can see how all of these things really do play into a good asset integrity program. Just to emphasize the importance of that in the United States, and this may be a little bit older data, but the important point here is that in the United States, it's been recognized that often some of the issues of citations, which means there's been some violation of a procedure, written procedure, training, inspection, or equipment deficiency. A lot of those are citations that go to companies within the US to say you need to do much better and you will be fined accordingly. This flow diagram might be a little bit busy, but what I want you to see is what we're talking about today as I bring my cursor is this mechanical integrity. Under that are many elements under that, and that's what we're talking about today. We're not talking about all these others that are important, but we're going to talk about written procedures, inspection programs, some equipment deficiencies, the applications of those to different types of equipment. Mike will be addressing some of that. Well, if you think about mechanical integrity, it could be kind of overwhelming. I think in earlier days, it was probably less comprehensive. It was kind of not as organized, not as documented. And so now you have all this documentation, which can be overwhelming. But it's very important, and it's very important that that information is passed on to the people who really implement that in your plants. Like I said, there's many tools out there. It might seem complex, but the main thing is to continue to move forward and looking at your equipment, having the right certified inspectors, doing risk-based inspections. That is more of a newer approach, looking at the higher risk issues rather than just doing a fixed equipment inspections. But these are all things that are very important. Just to build on the OSHA, what is also developed is a risk-based process safety, which took it to the next level. What that is, it's looking at more of the hazards and the risks, recognizing that not all hazards and risks are the same. So often when a risk-based approach is taken, It's looking at all the potential hazards and risks, but then prioritizing those risks that could be the greatest hazard or the greatest potential risk for loss of containment. And the focus, therefore, because many of you recognize you cannot do everything in a turnaround, you begin to focus on those that are higher. And so it becomes a prioritization methodology of getting there, just so you can accomplish those higher risks and use your resources to the best ability. So the CCPS, or the risk-based inspection, expanded that into 4, what they often refer to as pillars, and 20 elements, as you can see here in this listing. The pillars would be a commitment to your process safety, understanding the hazards and risks, and managing the risk, which is that aspect of asset integrity is part of that. And then learning from experience, and I've highlighted the asset integrity and the learning from experience under incident investigations, because later we're going to talk about a best practice related to investigating those things that occur in your plants. Again, now let's focus on the asset integrity, often referred to AIM. Again, we are looking at your equipment. It could be fixed equipment, it could be rotating equipment, it could even be controls of some of your equipment. But all of that is important to the operation of your plant, and therefore that all fits under your asset integrity program. Early in my career, probably about 20 years ago, I was part of a team that went to the North Sea to look at the asset integrity of multiple programs in place for offshore platforms. It was there that it became very evident of the necessity of that because of the hazards of offshore platforms, environments, and the corrosion and operations. And so that also applies to our land-based resources and assets too. So when we're talking about managing risk integrity and reliability, we're talking about the design, the installation, and all the activities that ensure keeping the equipment fit for its purpose until the retired appointment occurs. Now, we will make a note, and at least here in the States, there's a lot of aging equipment. And it's that aging equipment that presents some challenges, because often equipment may have been designed for 20 years or 30 years, and it's actually being used for 40 years. So you have to do those assessments if you're having that old equipment. That does not mean that new equipment should not be inspected or part of your program, but the greater risk is with your aging equipment. So when it comes to an asset integrity requirements, these are a few of the things. Mike's going to talk more about some of these, about pressure vessels, relief systems, shutdowns, controls, compressors. Again, we're probably a little bit partial, but we do believe mechanical integrity is one of the largest and most important elements of your PSM program, and may even be one of your more expensive ones because of having to put the resources into doing those inspections. As it comes to the company is wanting to ensure that all your maintenance and inspection personnel are trained to perform that requirement. When we have done audits at different places, one of the things we will do is we will check who's been doing your inspections, and do they have the right certification? Have they had the proper training? And do you have it documented? In the States, it's very important, not only that someone has done it, but you have records that they've done it, so that you can demonstrate that. Related to testing and inspections, it's just there. This is, again, Mike's going to address this a little bit further, but it's so critical that you have a plan in place and you're meeting the codes and standards and the recommended best engineering practices, and you are tracking through all of your equipment, where you can point to equipment of that heat exchanger, that vessel, to say, we know when it was inspected, we knew what was inspected for, and we knew that person was certified, and therefore we found some deficiencies, and this is the actions that we took. Concerning deficiencies, this is a big deal, because if you're going to do inspections of equipment, you are going to find things. And the challenge you will face is, are you going to be able to address those in a timely manner? And for the purposes of allowing that safe operations will occur. And do you have the necessary spare parts or new materials necessary? Like the example I shared earlier, a vessel had a repair well done that was inadequate, and therefore it resulted in a brittle fracture. So again, those deficiencies have to be addressed in a very appropriate way. Again, there's many people involved in a mechanical integrity program. It starts from the top, from your plant manager or your PSM lead, but the reality is the implementation of that goes down through your staff, to the operators, the inspectors, the millwrights, even some of your warehouse staff. Everyone needs to buy into your mechanical integrity program. And again, I threw up some of these pictures because these are things that we have seen that happen. The one on your far, looking at the left-hand picture, a failure occurred of a stainless steel pipe in a nitric acid plant that resulted in a launch of that pipe through the roof. Or you have a situation of a creep failure of a heater tube, or maybe a radiant tube, or a platformer. And so those are high temperature issues. And you might even have high temperature hydrogen attack, where you get fissuring or cracking, as shown in the far right. So these are all things that can happen and can be avoided, though, which, as we begin to think about those failure mechanisms, what we're really talking about is, do you have the right controls in place to manage your risk? And a good asset integrity program will know the likelihood of that failure and the hazard or consequences of the failure. And so the objective of your program is to control those risks, manage those risks, so that you can prevent those things from happening. And my experience has been, often it's the unknown that often gets us, because we are either not informed or we don't understand all the implications of what could happen. But once we understand those drivers for mechanisms that can degrade our equipment, we can then inspect for it and therefore reduce the risk. And so that's kind of what leads into the next topic, which Mike is now going to take over.
Thanks, Dan. We've gone through a lot of the results of not having a comprehensive asset integrity management program. Dan showed you some of the failures that occurred, and we're going to try to show you now tools that will help you take that. We just saw the 5x5 risk scenario, which I think is most, either 5x5 or 6x6 matrix, are the key and the cornerstone of most mechanical integrity programs. Those who operate in the high red region are subject to more incidents than those who operate in the lower left-hand corner in the green regions, which means you're basically in a controllable area where your likelihood is low, and if there is a failure, your consequence is low. You want to try to live in the green area, not in the red area. A few ways to start doing this. The cornerstone, I believe, of an asset integrity program for fixed equipment is a damage mechanism review. These are the foundation of the asset integrity plans. They try to go through equipment in a systemic program for addressing life-limiting and compromising damage mechanisms, both unaddressed, both that are known with the equipment, and hopefully you'll look to see what unaddressed or unknown damage mechanisms may have occurred in other similar units, either at your facility or other facilities, that can cause a loss in production. I've been fortunate enough to work in plants, as Dan had mentioned, aging equipment. The refinery I spent 25 years working in was built in 1908. So obviously we still had some equipment in service since then. Some of the utilities, I think the oldest vessel I worked on was from 1932. Some of the fixed equipment was there. So at that time, the equipment was well over 80 years old. Having said that, in the utility industry I worked in New York City, we had operating equipment still in service from 1888. So again, the refinery I worked in was relatively young compared to the utility, where we had wooden gas pipes and copper steam pipes. All those are still in service. We try to remove them. Throughout this methodology, I've been fortunate enough to write, to implement a lot and to write and present. And the papers you see listed at the bottom of this slide are available if you send in to Baker Risk. We can provide these for the damage mechanism approach, specifically for ammonia plants. Both Dan and I have presented papers on that. I've also done plant and circuit-wide CCD and IOW implementations for major refinery chains in the United States. And specifically, I've been involved for the last 10 years in applications for prevention of HTHA failures and the implementation of the new methodologies for non-destructive testing of HTHA. I was the program manager and lead engineer on a major international program that has effectively changed the inspection modalities and has led to new life prediction on HTHA. So again, those papers are all available. A mechanical integrity program must include pressure vessels, piping, relief valves, controls, the emergency shutdown systems, also known as safety instrumented systems, and pumps and compressors. The many will be handling the fixed equipment and the piping in this one. There are numerous damage mechanisms. These are just some of the ones in corrosion that you may encounter in your plants. Overall, the American Petroleum Institute API 571 has a list of damage mechanisms that I've been both an editor and am an active contributor to that document, which is in its third revision right now. There's over 75, possibly 80 now, specific damage mechanisms on corrosion and mechanical situations. We go through those in a very shortened version of what they are, what materials they affect, and how you could effectively mitigate or inspect for them. They're way too numerous to go into, but needless to say, you need a subject matter expert, which I would consider myself one of those, to go through and see how these damage mechanisms may apply to your specific equipment and where they may evident themselves. The way we do this is, here's a damage mechanism view of an ammonia plant. This is how I look at a typical ammonia plant. This is this is one of the typical hot ammonia synthesis plants by KBR. And you'll walk through the hot section. You'll see there's about 25 different damage mechanisms in the yellow flags that you'll see. Some are very specific to the equipment, and these aren't pointing to the exact drum or the exact location, but this is where these damage mechanisms may start to occur based upon the material of service, based upon the temperature or pressure conditions, based upon the condition of the installation, whether you have it or you don't have it, or some of the specific operating scenarios, whether you're in a single phase flow, whether you're vaporization, whether you're condensing. We walk through the plant and we see those, and a way to further drill down on that would be how you go about implementing a proactive mechanical integrity program. Usually includes a risk-based inspection review and a risk-based inspection program. You have a procedure manual, you'll collect your safety information, you conduct your damage corrosion analysis for each unit, which usually involves thousands, if not millions of TMLs, which are thickness monitoring locations. Sometimes they're called CMLs, corrosion monitoring locations. And what we try to do is break them down into a systemization and circuitization that we'll talk about soon. But the condition monitoring locations, try to capture the areas where you have damage mechanism locations that can be measured by thickness, and you develop inspection and test plans for the damage mechanism corrosion potential based upon the severity of that damage. Usually that's not based upon a time-based. Dan talked earlier about risk-based inspection versus time-based inspection. We're trying to move away from the time-based inspection, which says every 5 years I'm going to go out and take thickness readings. Some of the corrosion mechanisms that we deal with can happen in the space of a shift in a plant, which is 8 hours to 10 hours. Certain stress corrosion cracking methods, if you put in the wrong bolts, by the time you walk around at the end of your shift to look at that, they could have cracked and fallen out. And I've been privileged or unprivileged to have been in a situation in an HF plant where 3 of the 4 drain line bolts had failed, and luckily we caught the last bolt, and they were just installed in that shift, and luckily that prevented a dump valve from opening up. We'll collect the data and put them into an IMDS, inspection data management system. The system and circuitization is the key to not overdoing it, and to properly capture the damage mechanisms in a specific circuit or a system. What I've tried to do in my implementations, which I've done probably over 75 different risk-based implementations and or updating, or what we call evergreening. We'll divide it into the appropriate systems, interconnecting piping that's subject to the same set of conditions, process service parameters, and then we circuitize these. These are sections of piping that are exposed to similar process conditions, corrodants, expected damage mechanisms. They have the same kind of external coating and or insulation or lack of insulation. And each circuit is defined a corrosion circuit and formatted it for inspection isometrics. We'll see an example next on the next slide. Oh, no, sorry, I missed one of these slides. It's confused up. This is an IOW slide, which somehow got put in here. I should have caught that earlier. So this is an IOW slide that we'll be talking about later on as an output of this whole this inspection, is an integrity operating window where there are established limits for variables that can, when you exceed these variables, affect the integrity of the equipment. Again, this is a little bit out of place, but I'll catch up here. The integrity operating window tells you in a set of given a set of operating parameters, you've exceeded a parameter that that causes damage or causes corrosion or degradation in the material. There are a few different kind of standard of IOWs. One can be a critical IOW, which usually requires an alarm to the operator. A standard IOW may have an alarm, will have an alarm associated with it. Standard IOWs or informational IOWs usually have an email alert or non-alarm condition or communication. Right now, the screen I show you is some limitations that we have based upon the equipment number. It goes through the service, it goes through the materials of construction, and it lists the damage mechanisms that we're considering in the specific circuit to control our accumulation of damage from that specific damage mechanism. More on IOWs. Is a successful IOW program is a communication tool that that will allow proper communication between process operations and mechanical integrity personnel. The frequency and urgency of the communication is based upon the severity of the IOW. Critical IOW prompts an alarm, so you should have an immediate reaction to tell the operator you need to take action to prevent further damage. And again, information IOW or exceedances that may only be realized during a quarterly summary when you get together with the process mechanical integrity people and inspection folks to try to decide what areas need more attention in the forthcoming quarter, or what areas may be relaxed a little bit to focus on other areas of high risk. IOWs do not eliminate risk, but they try to minimize the amount of risk and push you down to the green areas. There's a corrosion control document also is another output of the API methodology on risk-based inspection. The corrosion control document is a repository summarizing the unit's process descriptions and its corrosion circuits. This is kind of the culmination of the systemization and circuitization that we kind of skipped over here, but it allows you to combine that with the key corrosion elements, how many mils per year or millimeters per year you're going through. The IOW in theory, the CCD contains the IOWs, lets you know what the high-low levels are, and the CCD is an essential part of risk-based inspection planning. It's covered in API 970, that's the corrosion control document. I'm going to digress a little bit. One of the key points of this is, from my experience, I worked in one refinery right outside of New York City area. The 25 years I spent in that refinery, I worked for 5 different companies. I never changed an office, but I worked for 5 different companies. Each of them had their own kind of management style. And some of those, we had good people who came and left. And what happens is, if you have a systematic program, such as API has documented with the RBI, the IOW, the corrosion control, regardless of what company rolls in, you have a congruency or a steadfastness, fixity of purpose of your inspection program that allows you to carry through different corporations taking them over. Again, that refinery had equipment going back over 100 years, and we found that relying on what we call tribal knowledge or the history of people working there may not be that effective because of the large turnover you have in companies. So we feel that implementing programs such as risk-based inspection, CCD, and IOWs are very effective to try to bridge that gap between transfer of knowledge and also looking to try to automate this information. The CCD IOW work process, we start with the process flow diagram, the corrosion loop diagram, where we define the corrosion loops based upon temperature and pressure changes, corrodants, other factors. We populate each loop, and we go through the process description, equipment of concern. The corrosion engineer will assign the relevant DMs to each corrosion loop with his rationalization for inspection and mitigation response. We try to list the key IOWs that I showed you earlier in that picture that we had associated there of a page of IOWs, and we try to maintain that we may not control the corrosion, but at least we're aware of it and its accumulation as we operate our units. Through that, we have key inspection and operation recommendations and concerns that we have. The next slide should show a picture of a crude unit. This is the basic unit of refinery. Again, this kind of looks a lot like the ammonia unit that we had shown earlier with the damage mechanism sticking through there. Once, here's a damage mechanism review, which is what we start out with, and there's about 20 in a crude unit. So what we'll do then is we'll overlay that with the next slide. And on the left-hand side, we'll show what that damage mechanism, the black and white damage mechanism review. On the right-hand side, this is what I call the finished product of a corrosion control document done well. We'll have the color-coded graphics, which makes it a very good learning tool. And the damage mechanisms, again, are included in here. They point to the piping and vessels. The colors show the different systems, how we've grouped the systems and circuits. And again, this is based upon temperature, pressures, whether or not there's vapor and liquid, whether or not it's all liquid, whether or not we have high flow regimes. And also the systems, the colors show the systems and the materials corrosion rates. And we have the different circuitization of piping. The piping is again, the color coded coming off of that. You go from one unit to another. Usually in the piping system, you'll have the same, either all liquid and vapor, or all vapor. You'll be insulated or uninsulated. The insulation presence changes the system, but here it's all documented on one sheet. For this particular process flow diagram of probably maybe 6 or 8 different pieces of equipment. and your CCD may be comprised of maybe 10 or 15 diagrams like this. This is the desired output of a CCD, which incorporates a damage mechanism review, the system and circuitization, the IOWs, and this is the finished product that can be used as a training tool or updated on a regular basis. So this is an ideal product where we're trying to get to. From that, we look to develop inspection and testing plans. And then these are looked to implement what are considered recognized and generally accepted good engineering practices, in addition to any specific PSM guidelines that you may have. Usually, ultrasonic thickness of each circuit of piping and equipment is used to collect the thickness readings to determine corrosion rates and look at the next inspection interval. What we mentioned, again, we're trying to get away from the time-based interval of saying I'm going to take readings every 5 years or every 10 years and go into a risk-based prioritization of what circuits do I need additional thickness readings on and what circuits do I need less. Some of these thickness readings can now be automated. Again, I was principal in a company that developed automated UT thickness readings that could go anywhere from low temperature up to 450 degrees C, and they could be applied permanently, take readings. You could take readings every second. You could take readings every month. It just depends on your battery life that you want to expend. And these give you continuous readings. The most accurate readings I've seen to a 10,000th of an inch. And then these need to be managed with an inspection data management software. You'll know a lot of these, Meridian, PCMS, there's a whole bunch of them that can manage your data. Usually they're tied in with a risk-based inspection program. And again, I didn't get into the risk-based inspection program, but there are a couple that can be implemented. Usually you have either quantitative programs. Quantitative programs would really rely on a statistical basis where you enter the pipe thicknesses, the diameters, the corrosion rates, the temperatures of the fluids. That's a quantitative, or there are other programs that are qualitative. A qualitative program requires a lot of input from a subject matter expert. And I know major companies like Shell and Exxon implement these qualitative programs because they have hundreds of years of experience captured with their subject matter experts. However, if you don't have that, usually a semi-qualitative or semi-quantitative program is what people usually find, bringing in a subject matter expert to try to handle the tribal knowledge in addition to some of the analytical work that the tools present you. Some of the concerns in mechanical integrity programs, incidents continue. Not every consequence can be identified in an MI program. PHAs, the treatment of MI issues, having been through hundreds of PHAs myself, I know we've probably spent 2 or 3 hours on mechanical integrity issues. Depending on who you have implementing that and who you have in the room, they can be spotty. So you really need your separate damage mechanism review, usually prior to a PHA, so you can bring your key concerns into that PHA in their limited amount of time they have to cover mechanical integrity. Again, we've discussed this over time. API has developed standards for improving equipment reliability, both in fitness for service, which is the 579 series, which has been adopted by the ASME and the FFS1, and also the risk-based inspection, which I mentioned earlier, quantitative, qualitative, but that's the key for implementing a mechanical integrity program that can be managed and becomes transferable to the next person. And again, here's a summary of the DMRs, IOWs, and CCDs necessary for asset integrity program. 571 is the damage mechanism, which I consider the key cornerstone for going through mapping, finding the right areas, monitoring them in a practical, judicious, economical approach of equipment management. You take those and you put them into the IOW CCD program, which again starts developing integrity operating windows to help you effectively monitor the standard operating procedures of the IOWs that can have your damage be accumulated in a controllable fashion. And then you roll all those into a corrosion control document. And that is a very comprehensive program if well implemented for a refinery or a chemical plant. We'll go into understanding the damage mechanism is the foundation for plant reliability and safety, as I've said a few times already. It's the basis for action to minimize, prevent damage mechanisms. Inspection planning needs to be effectively implemented. Too much inspection means you're spending too much time on just entering thickness data as opposed to looking at what the effects of that thickness data are. I know some refineries in the United States had over 3 million TMLs, which is a major project in itself just to try to do those 3 million TMLs in a yearly or a bi-yearly process. Rather than taking thickness readings, you need to be looking at what's going on with my damage mechanism sites in the key locations. You also need to stay within the guidelines of your regulatory business incentives, of legal, what you need to prevent loss of containment. And the basis for process safety is asset integrity, looking at your material construction review, HAZOPs, and then use those CCDs as a training for your process engineers to your operating personnel to try to have them effectively learn the history and what they need to be concerned with as they're operating their unit to maximize the quality and the quantity of product that they're producing. I'll turn it back over to Dan right now, and he'll go over some of this specifically applied to an ammonia and fertilizer program that Baker Risk is very proudly the steward and the mentor of.
Well, thank you, Mike, for sharing some of your wealth of experience in your career as just as a subject matter expert in doing the things you have done. We wanted to share with you an example, a real live example of an application of an asset integrity program, in essence, as we have been working with the ammonia and the fertilizer industry right before COVID hit. We have been very involved with the ammonia and fertilizer industry for many, many years. And prior to COVID, we meaning Baker Risk and also some of our staff presented this as a suggestion. And therefore, what we did is we did exactly what we were talking about, is identifying what are some of the damage mechanisms as well as mitigation options for equipment for the purpose of increasing reliability. This program has been a global program, and we have been very, very pleased to represent many of these companies, some of which I'm sure you are familiar with worldwide. It is a global program. We've completed our 3rd year, and we've done 7 different studies. To become a member, it's a kind of select membership. There's a fee, and then you get access to some of this information. But our objective was to share knowledge and the lessons learned so that these incidences can be avoided. One of the things we've heard, and maybe some of you are experiencing too, is there's turnover in staff, and some of that tribal knowledge that Mike referred to is getting lost. So therefore, you've got to have a system in place on how to capture that. And so the ammonia and fertilizer joint industry program has been one way where we've identified many damage mechanisms, as Mike had referred to earlier, and some of the key processes, which include the ammonia process, storage tanks. We've also looked at the urea process. We've looked at ammonia nitrate process and nitric acid. All of these have very distinct damage mechanisms and are important. As an example of that, this is just an example of how we applied some of the things that we learned about a damage that occurred in a storage tank in 2011, where the reality of the situation is ammonia stress corrosion cracking is a known phenomenon that can occur. And the issues at hand with that are the ppm of oxygen and the amount of water. If you see this curve over here on the left, you can see if your oxygen level is too high and your water level is not high enough, you can potentially have a risk of stress corrosion cracking. So what do? Well, you make sure you have enough water and you make sure you don't have oxygen in your system. But in this particular case, you can see some cracking that occurred. And the reason it occurred is if you look at this little chart above there, in 2007, 4 years earlier, the water level had gotten low, much below the recommended minimum percentage, which is about 0.2% weight percent. And so this is just an example of the importance not only of monitoring, but knowing when you have situations when, in this particular case, a contributing factor such as water level is below would give you an indicator that you potentially are at risk for cracking, as seen here. So again, that's just an example of how the ammonia fertilizer JIP is taking real lessons learned and applying that. Our final point that we want to discuss with you is what we would call a best practice. We have been working with many companies around the world, and with that, this is a best practice that we have seen utilized by some, not necessarily all, and that is trending near misses or failures are often referred to as precursors. And what the reason you do that is to, again, better understand the potential issues that could happen. So if you look at this pyramid here, the statistical basis of it, that for one fatality, there is potential 3,000, for example, near misses or 30 recordable injuries. And so what the thought process is, if I can identify some of these less severe cases, then I statistically am at the possibility, will have a greater chance of avoiding the major incidences as described before. So again, so we're looking at the precursors, trying to trend those, and so that's the emphasis, trending those, learning from those. The dilemma you will face is just the fact that they can happen, and then there's a challenge of, well, do I really need to investigate? It takes too much time, it costs too much money, or who's qualified to investigate? But the greater purpose, and I've seen this at companies, is management has recognized to avoid that major incident, it is worth the investment to trend those potentially less severe minor incidences so that you can keep the material in the pipe. And so a lot of the premises behind this is that almost always there's a less severe precursor before a major. There's always something that, like the tank, the precursor in that particular situation was the water level was low. That would be considered a failure of the monitoring system, in the fact that it went down and it wasn't addressed. And again, you can prevent that as you identify those contributing and potential root causes. And this is an example of the paper that we presented that is a good example of a best practice, which we can share with you later on. Again, back to the precursor mentality or near miss. Again, it is something that doesn't seem to be very significant, but the reality, it could have been very close to being very significant, or possibly a close call, a near miss, a near hit. Again, we see that this is a best practice. We recognize this. We have seen that incidences have been avoided when this practice is adhered to. Interesting enough, Mike referred to API, American Petroleum Institute. There's another recommended practice, 585, which we have had input into, we meaning Baker Risk. And the industry saw the need to do investigations systematically. And therefore, it put this best practice out there to avoid a scene like you might see in this picture, which again we were involved with. And so if you do not have that resource is part of your resources of looking at investigations, I would highly encourage you, and we can discuss that with you if you would like. Again, part of that document is to look at your pressure, mostly your pressure equipment, which is often referred to as PEI, to avoid those, and to make sure you're within your regulatory requirements, and also, again, just so that you're operating very safely. Excursions, what are some examples? You can have excursions of process parameters, like I mentioned with the water. You might have temperature excursions, pressure excursions, all kinds of things. You could have layers of protections fail that need to be maybe an indicator of something going on in your system, like a rupture disc corroding might indicate that it failed because you have some contamination in your process stream. So these are just a few things, just a suggestion of things that could be considered precursors. And again, precursors often are things that we're unaware of sometimes, and it requires good discipline actions. And we wanted to address, it becomes also a plant culture thing to develop that safety mentality that any kind of incident, although maybe minor, really requires investigation so that you can understand what is going on. But we believe there's good value in that, even though there might be a small equipment failure. The end result is it prevents that ultimate event from occurring. I mentioned an RV, a relief valve, pressure relief valve. We've been involved in a couple incidences where the relief valve has been corroded, therefore stuck, and as a result of that, it doesn't do its job. Many of you are familiar with the Swiss cheese model. Looking at it this way, basically there's that hazard, and an accident could occur if these layers of protections are not in place. And one of those is just looking at those precursors that will reveal the potential layers of protection. Again, it's just another way of preventing that from happening. So the final points that we want you to take away is that a good asset integrity program is a must. If you're wanting to control your risks, we've gone over some of those elements. It starts from the top within not only your government, but your plant managers and your executives, and then it is implemented by those who are doing it day in and day out. It's a written down guidance. And we believe that two things that are essential to a good asset integrity program as presented today is having a good damage mechanism review and trending some of those near misses or precursors. So that concludes our talk. There'll be some slides and some of our other capabilities, but for now, I'm going to close and address any questions.
Thank you so much, Dan. So I'm going to go ahead and ask some other questions that did come up during the presentation. And just as a reminder to our attendees, if you have not already done so, please be sure to type your questions into the Q&A box in your control panel. So first question, Dan. What are the major differences in the use of qualitative methods in risk analysis in comparison to the quantitative methods employed for this work?
Yeah,
Dan,
Mike
I can
mentioned
take
it.
that.
Yeah, go ahead, Mike. You mentioned that earlier.
There's since the mid 1990s, there have been a few different systems of leaving the time-based regime, which is saying we'll inspect every 5 years, we'll have an annual shutdown to look, and the risk-based inspection, saying what is my next piece of equipment that's going to cause me an issue. There are two different schools of doing that. As I mentioned earlier, one is a quantitative, which is a statistical basis. It usually takes a lot more time prepping for that. Again, it requires a detailed list of materials of construction, thicknesses, diameters, pressures, temperatures. But I believe it yields a very good basis for any program you may want to implement after that. It is a lot more upfront to do that. Other companies come in and do their qualitative. As I mentioned, I'm familiar with the Shell RBI program and Exxon and other subject matter expert-based programs, which are more qualitative. They may change with the subject matter expert you have in, which is something that a quantitative program doesn't do. But depending on the experience and the quality and the knowledge of that subject matter expert and the information you've provided that subject matter expert, that can be a very good system also, but there's a lot more areas for failure. Usually there's a combination between the two. API, RBI is something I've been familiar with for almost 20 years now. That kind of gives you the semi-quantitative approach, again, with the implementation of a subject matter expert, which seems to be what the industry I've found, and the global industry has kind of come to as a very good middle ground that doesn't require specifically on subject matter expert, nor is it that data driven for equipment condition and initial input to get the program started.
Great. Thank you so much, Mike. I'm going to go ahead and ask one more question. Is piping a necessary component in the overall fixed equipment mechanical integrity strategy?
Dan, I can grab that one also. From my experience in 30 years in process piping and power plant piping or power plants, and this is backed up by some Exxon statistics, over 85% of our leaks have occurred in piping. We do monitor our pressure vessel and our pressure equipment very well. They have name tags. If you strike an arc on them, you need to record that. The pressures are set and controlled by safety release devices or rupture disc for pressure equipment, drums, towers, vessels. Piping is probably where most of the incidents have occurred in my experience and also the global experience of Exxon. So over 85% of the leaks we have occur in piping. Hopefully, many of them are just nuisance leaks that are flange tightness or other issues. However, if you have most of your leaks occurring there, you're going to have major incidents occurring from piping. And I believe piping is something that usually gets addressed last in a mechanical integrity program, but that's where most of your incidents do occur. The pressure vessels, pressure equipment are easier to implement into an MI program, and a lot of the integrity hardware is already there. You know, you have your thicknesses, you have your recorded incidents, but we're ignoring piping. And again, probably 50% of the leaks in piping have occurred due to CUI, and that's corrosion under insulation. So that's in plants. So if you were to ask me to predict where the next failure in any process plant would be, I would say it's probably from a CUI incident occurring in piping that hasn't been looked at because you thought it was good system. So those are the major areas from IC that have been put on a lower priority, but they cause more of the leaks. It's in piping and it's in CUI.
Great, thank you for that. So it was mentioned that aging equipment in older plants should have good asset integrity management or the AIM program. So what about new equipment, and how important is it to have new equipment in an AIM program?
Naomi, I'll handle that one. I think we mentioned that aging equipment is a big concern because of the exposure over time to various damage mechanisms. However, it is critical as you start your AIM program to establish a baseline for your equipment, so that as your equipment continues to age, you have not only you get a progression, an assessment of that. And also, just because it's new doesn't mean it's not subject to some of these damage mechanisms we've discussed. And so therefore, it's essential that both new equipment and aging equipment should be in your a good asset integrity program.
Great. And how can key performance indicators or KPIs be used in an AIM program? What are the advantages and limitations of using those KPIs?
Yeah, I'll address that question also. We didn't really get into key performance indicators in this particular talk, but my experience is you have to have certain indicators to know how well you're doing, and your asset integrity program will often set those up on what you're measuring, how well you're doing. The potential limit, and I know this is just not necessarily has to be the case, but sometimes if you know what that key performance indicator is, you might overemphasize that and miss some of the other things that are important too. And you might even have a false sense of security that you're really operating safely when in reality you may not. So you kind of got to weigh that again, you need to evaluate how well your equipment's really doing, and don't just hold on to a KPI as the only evaluation tool.
Okay, thank you for that. And I'm going to ask one more question before I reintroduce Wayne. So it was mentioned that dead legs and piping should be monitored in an AIM program. Can you elaborate on what that involves and why it's important?
Again, I'll start with that. You know, dead legs is in essence a piping system that is you for a period of time you might not have flow going through it. Therefore, it's called a dead leg, or it's not always in use. And many of the incidences that have occurred, and I've been involved with myself, have been in dead leg scenarios where it was unknown, and the thought was, well, it's just dead and there's not process. But the reality is there's a lot going on in that dead leg, and therefore often a robust asset integrity program would have a dead leg program of some sense. Mike, what have you experienced in your career on dead legs?
Dan, let me go unmute this. Am I live right now?
Yes,
Yeah,
you are. We can hear you.
Sorry about that.
That's okay.
My first major incident in a refinery was with a dead leg in a FCC light ends unit. It was handling light ends, and it had a dummy support. That is a piece of live process piping that was run off to just do nothing more than support that piping. Well, that leaked and it released C2, C3, C4s. I was driving through a major five-lane highway right outside New York area, where the entire highway was shut down because it was engulfed in the flame from that incident. So that has driven, in addition to damage mechanisms, there are now areas called LSDS, localized specific damage scenarios, where we have corrosion occurring in carbon steel piping, but you need something very specific like a dead leg, or a dummy leg. There are also injection points and mix points, areas that have material that may itself be non-corrosive, but certain conditions exist either periodically or continuously or on a sporadic basis that causes damage mechanisms. So these are not continuous damage mechanisms, they're intermittent, and they may be intentional, like an injection point or a dead leg. And those are getting better attention, either trying to eliminate them in design, which is the importance of doing pre-startup pre-startup RBI type analysis or damage mechanism reviews, or in addition to adding equipment in or changing equipment. So dead legs have been in my refinery a specific problem for over 40 years that have been hopefully eliminated as much as possible through design and through review of incoming piping, but they continue to cause problems throughout the industry, and API is now addressing that in their latest revision of 571 under the local specific damage mechanism scenarios, or LSDS. It's moving it up to another level for more attention.
Thanks, Mike.
Thank you both. Thank you both. And so, Wayne, I would love for you to come back on and hear some of your remarks and insight, please.
Sure. Thanks, Naomi. Thank you, Dan and Mike. Great presentation. Appreciate that. I hope everybody enjoyed it. I'm looking at the questions throughout, and we've got a lot of questions here.
Mhm.
As mentioned, we are going to recap those. We'll get an email out to you in the next 2 weeks with the Q&A, along with the presentation itself and any other resources that we have discussed during this session. I do want to have a recap from Amr Hassan. So Amr, if you can add your thoughts on this and on asset integrity.
Yeah, thank you, Wade. Thank you, Wade. Thank you, Dan and Mike, for this very informative session on the asset integrity. I just want to recap a very high level in 3 points. First one is to stress on the trending for the near misses. And we know, of course, the challenge and the resources. So I would suggest for those who want to train the new methods to just to follow the risk-based approach. If the reoccurrence of this specific near miss has a potential for major consequences, so we can investigate and trend more to avoid reoccurrence. So applying the risk base, it will help you to have some resources to investigate and trend the near misses. This first thing. The second point is the link of following or working within safe operating limit and asset integrity. I have seen some cases that working outside safe operating limit can cause severe asset integrity issues. So when we investigate the working outside safe operating limit, the team should look to the link to the asset integrity. And the last point I want to also address is the most of the asset integrity expectation and requirement, which Dan and Mike mentioned. It is listed in the operation performance standard for safety critical element. So I have seen many companies, they have a great performance standard, but simply is not followed. So if we really follow the performance standard, both the assurance activity and verification activity, I believe it will help in to a very high extent to have a proper and in place as an integrity program. That's it.
Great.
Thank
Thank
you.
you, Amr. I appreciate the comments. Again, thank you to everybody. Thank you to the ministry for their support on this. We are going to be looking at offering a course on asset integrity later on this year. We don't have dates set on that yet, so please keep an eye on our website. We'll also be posting that and putting out more information on LinkedIn, and if you're in our database for our mailing list, you'll see it that way as well, our newsletter that goes out monthly. So with that, thank you to everybody for attending, and Naomi, I'll let you close it up.
Well, thank you again, everyone. Wonderful presentation, already great feedback from our audience. So as a reminder to our audience, if you do have any other questions, we ask that you put those in the Q&A box. And as Wayne mentioned, we will get those posted and out to you guys. And as a reminder, fill out the survey that does come up at the end of the webinar so that you can provide your feedback and let us know of some topics that you're interested in. And be sure to subscribe to our Baker Risk newsletter so you can stay in the know of what we're offering. And then our next webinar will be in November, so be on the lookout for that information coming to you guys. So again, thank you, everyone. Dan and Mike, great job. Wayne and Amr, always appreciated. So have a great day, everyone.
Thank you, everyone. Bye.
Thank you. Bye-bye.